desktop or a laptop?
Laptop.
Yeah, me too.
My cameras are fine. It's just like sometimes the RAM is like.
Gotta have a strong computer. I remember.
I have an Asus. It does the work.
I remember when I first was interested in like architecture engineering, somebody told me, get a MacBook. It'll help. Yeah. And then I entered college and I was like, yeah, I'm going to get a MacBook. And Professor Neiman immediately told me, don't do that. AutoCAD's not compatible with Mac. And I was like, what? And she was like, yeah, they have a Mac version, which is crap.
When I was an engineer, I knew people who had MacBooks. And I was like, I don't know how you're doing this. So you can't use Python with Mac. It's an entire different software.
Can you use MATLAB?
I didn't use MATLAB.
No?
In my class.
It's the main thing that we have here. Because it used to be C++ back when the old chair was here. Oh, God.
I hated Python. I hated it.
I have funny stories from that class. I remember I hated that class, so I would always troll him in my assignments. There was one time where he had us create a game. It was basically, it produced a random number, and if you guessed it right, you win. But I added a catch. I put it to where if you guessed it wrong, it would immediately delete System 32. And he caught it before he ran it, and he was like, this isn't funny. I'm giving you a 75 for this. And I was like, I'll take it.
Are you good at coding?
I was terrible at
I'm pretty good at it.
It's so confusing.
it. Luckily, the person who sat next to me was a good coder. So
Anyone can be a good coder. Just ask ChatGPT to do it for you, and then just modify it as you need. That's what I used to do. Well, that was actually, I used to have to code by hand beforehand.
that's good. I just watched videos. I found some guy who like taught the whole course, and I was like, okay.
Yeah. When I was learning the finite element method, that's like the software that I use, but we had to code it by hand in grad school. I found an old like 1980s textbook with codes in it. I took those, just copy pasted them. Yeah. They might have been in Python, but like, fortunately I could like convert it somewhat into like MATLAB and make it work, because that was the software that we used. So, yeah. I still have stuff written on here for some reason. Let me delete it. Remove this. And I guess nobody else is coming today, so I'm just going to go ahead and hop straight into it. We're still...
Giving up or something?
I don't know. 2 students emailed me that they weren't going to be able to. And 1 student, I have no clue. And then Thomas is still on the cruise, I think. I don't know how you can take a cruise mid-semester, but okay. All right. So we're just going to be doing more practice today of like shear force and moment diagrams, and then also like the design of beams, and then the analysis of beams. So what I want to do is just give you guys a little sample here. Let's say that this is 3 feet and 8 feet. This is a, let's see, what's a good shape? A W8 by 58. And so A992 steel. So using a factor of safety of 1.6, no, 2.0. I want to use 2. Determine if design is adequate. All right. So, is at okay for flexure, because we haven't learned about shear yet. and I'll probably go into shear next class. So I'm going to give you guys a few minutes. Just recall your equations from last class. Determine what your moments are, your diagrams. You can either calculate what the bending moment would be using the tables, or you can do it just straight up by hand, draw the shear force, and then calculate the bending moments. And then from there, just determine if this section is adequate for the load. I'll give you guys a few minutes to do that. You guys figure it out yet? Maybe? What'd you get for the W shape?
Well, that's what, is this for the W shape? I just wanna make sure I'm on the right one.
Well, it should be a W8 by 58.
So that,
Yeah.
so then it's this times 2, and that's this thing, so then it's good.
What's your section modulus you're getting that you need? Here, let's work on it together. I was just messing around with some stuff on here. So let me pull that back up real quick. All right. So, is the W shape adequate? I want to hear what you guys got. Michael,
I'm still solving.
still solving. Did you figure it out? You think you got it?
I don't know if it's right, but I think yes, but.
All right.
I don't know if it's right.
Edgar?
Don't hope I got it.
All right. Haza? No? Oh, this is bad. Your exam's in like 2 weeks. It's before Thanksgiving. All right. So, let me ask you guys, what did you at least get for the bending moment? Did you draw how did you guys do it? Shear force bending moment diagrams? Did you draw those out, or did you just use the equations from the tables?
I don't know.
What?
I don't know.
All right. Well, what you could have done is you could have used figure 8 here, because that gives you the bending moment for this load case. Within that table, A is going to equal 3 feet. B is going to equal 8 feet. The length is just going to be 8 plus 3, so 11 feet. And so when you plug this in, you get M max is equal to the 20 kips times A times B divided by L. So 3 feet times 8 feet divided by 11 feet. All right. Now, what we should get for the bending moment is 43.6. 64 kip feet. Is that what everyone got? Now, we need to design our section for a factor of safety of 2. So what does that mean? Our design bending moment is just going to be M max times 2. So this gives us around 87.27 kip feet. From here, what do? We need to calculate the stress in the beam, which is going to equal what? What is our stress equation? M over S. Keep consistent units. So you have to multiply 12 inches per foot, so that way the feet cancel. And then what's the section modulus of a W8 by 58? Is it 52? Yes. Over 52 cubic inches, which gives us 20.14 KSI. So is our design adequate? Well, what's the yield strength of steel, of A992 steel? It is 50 KSI. So because our applied stress is less than sigma y, what does that tell us? Good or bad?
It's good.
Passes. Great. Pretty straightforward, right? All right. That's how you perform a design check. It's just really getting good at drawing these diagrams and using these tables, and then just remembering that equation, sigma is equal to m over s. Does that make sense to everyone? All right. Now, let's see. Let's see here. Here we are. Now, there is one more topic that I really want to discuss in terms of beam flexure, and that is composite beams. Now, for composite beams, what do we know what a composite is?
Two or more materials.
Yeah. So this could be like a wood block with maybe some type of steel. So again, a composite is two or more materials. Now, when we were learning about composites for axial loads, how did we relate the composite materials one to the other?
They were both equal to one another? Like they,
Well, that was compatibility. The strains are equal to each other. I'm not going to go into the derivation for that because it's kind of hectic. I'm just going to show you guys like an example problem for where that would be used. But what I do want to ask is, like, there was a material property, there was a property that we used to relate stiffness of one material to another. Do you guys remember Poisson's ratio? No, it's not Poisson's ratio. It's the modular ratio. It's the ratio of one material over another. You guys remember doing this? Now, this becomes really important. So, let's say that just for simplicity's sake, just to simplify the problem, let's give this problem some dimensions. Let's say that both of these elements are the same dimensions, right? I didn't exactly draw them as such, so let me fix that really quick. There. And let's assign 2 inches, 1 inch, and 4 inches. Let's say this has an elastic modulus of around, I don't know, 1800 KSI. And then this had an elastic modulus of 29,000 KSI. So, the way that we would solve this is we would still need to use our equation sigma is equal to my over I. You would need to use this equation because it's not symmetric. You guys remember this? When I said last class we can use the m over s equation for symmetric shapes only. Otherwise, you need to use my over I. This is one of those examples. So, what we need is I and Y. What is I? It's the second moment area of inertia. So what you need to do is create that table, if you guys remember this. That gives you the location of the neutral axis. And then you're going to have an IX, a DY, an ADY squared, and then an IX. Do you guys remember doing this in statics? You do? All right, that's good. All right. Now, what are our two components? We're going to have component 1 and component 2, the blue and the red. However, one of the things that we need to do is make all of the materials, quote unquote, one equivalent material. The way that this is done is by taking our section here and finding a geometry that meets an equivalent stiffness. The way this can be done is by simply transforming our stiff section into something more equivalent to in geometry, such that it meets the same stiffness properties. I'm not grabbing it properly. The way that this is done, I'm not going to be able, I got to erase that. What we can do is then change the width here and this width that we change this geometry to is equal to that dimension that we initially had, which is just going to be the 2 inches, and then we multiply it by this value n. Now, in this case, E1 is going to equal 29,000 KSI, and E2 is going to equal 1,800 KSI. So 29,000 divided by 1,800 gives us a value of around 16.11, which means that this width is equal to 32.22 inches. It means that in order to meet the equivalency of this steel, you need about this much amount of whatever material it is. I think it's like wood, okay? Let's say it's wood. So the blue will say is, whoops, I don't know why it just shot off like that, but this is wood, and then this is steel, and I'll actually clarify that down here. So wood, and then steel, but we want to use the wood equivalent properties. Now, all we do from here is work this table using this updated geometry. And then the vertical dimensions here just remain constant. So that stays at 4 inches. And then this height stays at 1 inch. Are there any questions so far about what's going on here? We're just relating one material stiffness to another and quote unquote transforming it because the variation in the stiffnesses are going to cause variation in stresses. Does that make sense? So the area of the wood for the top is just going to be 8 inches squared. And then for the steel equivalent for wood is just going to be 32.22 inches squared. What we need now is the neutral axis locations. The neutral axis locations, if you guys remember, is just taken with respect to the bottom. So for the wood is going to be 1 plus 4 divided by 2, so 3 inches from the bottom. And then for the steel equivalent, wood is going to be ½ an inch. Lastly, just multiply across, you get 24. And then 32.22 times 0.5 is the 16.11. And so you just sum everything together. This becomes 40.22, and this becomes 40.11, which means that our y bar is equal to about, ironically, it's equal to roughly an inch. It's very close. It's like 0.998 inches, but I'm just going to say it's 1 inch. From here, you do dy. dy is the distance from the neutral axis, which is just going to equal y bar minus y bar, we'll call this y bar t, so that's going to be this. And you're just taking an absolute value of it. So for the wood, it's just going to be the 1 minus 3, so this becomes 2 inches. And then 0.5 minus 1 inch is just 0.5 inches. 32.22 times 0.5 squared gives us 8.06. And then 8 times 2 squared gives us 32 square inches. And then Ix we calculate using the known value bh cubed over 12. Which for this, it would be, for the wood, it would be 2 times 4 cubed divided by 12, which gives us 10.67. And then 32.22 times 1 cubed divided by 12, which gives us 2.69. So this is 40.06, and then 10.67 plus 2.69 is 13.36, which means that our total second moment area of inertia is equal to 53.42 inches to the fourth. We're not done with the problem yet. All right. Now, let's say that this beam, we do our analysis, and we have a design force of M equal, I don't know, 40 kip feet. All right. If we want to determine the stresses at the top and at the bottom, we need to use the my over I equation. So 40 kip feet is the load times 12 inches per foot to convert it from kip feet to kip inches. Y is the location from the neutral axis. So let me grab this diagram again. Whoops, why am I typing E? And that wasn't even what I grabbed, but anyways. So our neutral axis was roughly around here. So y bar to the top, that would be just this value. Conveniently was 4 inches. And then y bottom was equal to 1 inch. The neutral axis isn't always at the location of transition. If, for example, you had two materials like this, You could technically have a neutral axis like here, for example, in which case then this would be y bottom. And then this here would be y top. But for this problem, it just happened that it's like pretty close to the transition point, okay? So y top is equal to 4 inches. And then we just divide this whole thing by 53.42 inches to the fourth. And what we get is 35.94 KSI. For wood, this is a very high stress, so clearly you would want to redesign it. Now for the steel, you do the same thing. But it's a different material. So for the transformed material, the steel, you need to multiply this stress by N. And this gives you a stress of around 144.75 KSI. I chose a really horrible bending moment for the checks, but you guys can kind of see what we have to do. Does this ring a bell to some people with like the second moment areas of inertia and so on? Or not at all? Okay. That's just how composites work. I might not give you a full-fledged problem on an exam. What I might do is ask you guys find the equivalent transformed section, which then would be just this entire thing in one problem. Or I might give you guys the material properties, including the transformed section modulus with a cross section. So I'd give you IX and the location of the neutral axis, and I would just ask you guys to find the stresses. So it would be like basically either this up here can be one problem or this down here can be one problem. But I won't give you guys both sections and one problem because it takes too long. We just spent 15 minutes doing it. Yes?
If that's on there, would you give us a table or should we write it down on a flashcard?
I would recommend you guys write it on a flashcard. It's because you don't technically need a table to do this, but I would recommend you guys know how to write it. I preferably don't put it on the flashcard, just remember how to do it. And actually, just as practice, I'm going to give you guys an example, and I want you guys to do this. Instead of it being a composite section, so don't transform anything. This is all one material. So this is 1 inch, 1 inch. This is 4 inches. And this is 4 inches. I want you guys to find the second moment area of inertia about the XX axis. All right, so that's like a bit of statics review for you guys. You should know how to do this. There's no need for a transformation of a section. That's just explicit for composites. All right? I'm going to pause this just really quickly, just so that way you guys can get familiar with it. And then I'm still like technically working on your homeworks because I forgot to make it. That, and I realized like we're kind of running behind schedule from what I wanted, but it's okay. Yep, so I'll give you guys, you should be able to do this in about 8 minutes, I'd say. 10, longest. figured out?
Okay.
All right. Somebody's got it, so let's go over it. Don't mind this. I'm just trying to plan for the next upcoming classes. All right. Shake this around a bit. All right. So, what you do, you make your table. Why is this on? A, Y bar, A, Y bar. All right. Your area is going to be in inches squared, inches, and inches cubed. And what you need is two components, your flange and your web. What was the area of the flange?
Which one is the flange for you? That's the top part, right?
Yeah, the flange is always the top, the web is always the centerpiece.
So the area for that would be 4
Yep.
inches squared. And the same thing for the bottom.
All right. What about Y bar?
I said 4.5 for one,
4.5 for the flange.
and 2 for the web.
Yep. And then a Y bar for each.
18 and 8.
All right. You sum these, you get 8 and 18, 26. So what did you get for your neutral axis location?
3.25.
All right. What that means is 3.25 inches from the bottom is our neutral axis. It probably looks closer to like something like this, I want to say. Maybe this. Whoops, I accidentally grabbed that on accident. All right. Good. Now, you've got dy in inches, a dy squared in inches to the fourth, and then ix in inches to the fourth. What'd you get for dy for each of those? Or you didn't get up to it yet?
Oh no, I did. I just messed up my Y bar. But
Mm.
I did 4 times 4. I meant to put 4 plus 4. It was just an easy fix though. So I think it should be 1.25 for the dy. I'm pretty sure it's for both of them.
And yeah. All right. And so then 4 times 1.25 squared gives us 6.25 for both. And then for the top flange, it's going to be 4 times 1 cubed divided by 12. So basically 0.33. And then 1 times 4 cubed divided by 12, which is going to be 5.33. You add these together, you get 12.5 and 5.67, which means that your total IX, you should have gotten 18.17 inches to the fourth. Yes?
Quick question, to get that Y bar, you divide 26 by
8.
8, you get 3.25, and then once you have that, what the dy,
dy, you can like, I'm going to call this y subscript I representing each component. Actually, the y bar of each component, so C. What dy is just going to be that y bar minus yc, but just take the absolute value because it ends up getting squared anyways, so it doesn't even matter.
so it doesn't matter the sign of the
Yeah. Because you notice a dy squared, the square is going to cancel out the negative.
Oh, man.
So just take the absolute value, it doesn't matter. All right? So you've got Ix total. Now, let's say that you have a beam and you do your bending moment diagram, your analysis, and you get that your bending moment is equal to, let's say, 15 kip feet. What? Actually, nope, I'm going to change that. Let's say that this steel is A36 steel. What's the yield strength of A36 steel?
KSI.
36 KSI. All right. So knowing this, what is the maximum permissible bending moment that this section can handle? Take a few minutes to figure that out. And once you guys figure it out, we'll take our break. Or I'll go over it then, we'll take our break. Are you guys understanding the topic so far? It's just the stuff with the IX is probably like a slap in the face because it's, you haven't seen it in a while. So my recommendation would be get familiar with it. And once one of you gets something, just let me know. I'm about to upload homework 8 to Brightspace because I needed to create a new one. Visible. Yes.
To find the elastic section modulus, would you use h squared over 6?
Not quite. So here's the thing. What you need to do is use the my over I equation because the section modulus is technically only applicable for the top part and bottom part independently.
Right.
So for this section, how many parts are there? It's not symmetric, so there's going to be 2 section moduli, which means you would need to calculate 1 for each. A simpler way of doing it is you know what I is, so just do sigma is equal to my over I, rewrite the equation, and then just put y is equal to whatever this height is, y is equal to whatever that height is, and then you find your capacity. Does that make sense?
Yeah. A little bit.
We'll go over it in a few minutes. Just promise you, just work it out.
All right. Thank you.
And just a reminder, homework is due today. So if you didn't submit it yet, please do so now. And then I did upload homework. What? Oh, yes. Here you go. Yep. You remember your stress equation?
I was trying to remember. I was looking back at my stags notes for his.
Here, I'll write the equations up on the board. Those are your equations for beam bending. Would you guys like me to start writing the equations on the board from now on, just to like help you guys? All right. Just remind me to, because otherwise I probably will just forget. But I will try to remember it. You guys figure it out yet? Maybe?
Yeah.
What'd you do?
I did sigma equals my over I for both, like you said,
Mm-hmm.
and then I found m.
Yes. How'd you rewrite it though?
I can show you.
Yeah, let's see. Because if you got it, then you just gave everyone a free break. Otherwise, we're working through the break. Wrong units, but looks right.
What units would you say?
So it would be in kip inches, which then usually if you're presenting that to somebody, you would just divide by 12 to get to kip feet.
Okay.
So yeah, looks right. Cool. All right. Let's unfreeze this. I gotta shake my screen just to turn it back on. All right, so M max is equal to question mark. How do we do this? We gotta recall our equation for stress. However, we write it in terms of sigma I over y. Now, because we don't have a singular section modulus, you keep the equation in this form. So, from here, you plug in 36 KSI times I, which is 18.12 inches to the fourth. But then the trick becomes, what do you use for y?
I used the 1 inch for the replacement.
Well, it wouldn't be 1 inch. So there are two possibilities that we can have for y. We can have y be this, y top, which what is that going to equal? And then we can have y bottom, which is equal to that. Can somebody tell me what those are equal to?
Is that y bar?
Well, y bottom is y bar, yeah, so 3.25 inches, which means that y top is going to be 5 minus that. So 1.75 inches. So, to find the maximum capacity that this section can handle, which value would you guys use? 3.25 inches or 1.75 inches?
3.25,
Why?
because it's the furthest away.
It is. You would use 3.25 inches. The reason for that is because when you are drawing your stress strain curves, your stresses will look kind of like this, which means the bottom is going to yield first. Otherwise, what happens is if you set the top equal to yielding, your stress diagram ends up looking closer to something like this. Which is incorrect. The reason being is because all of this also ends up yielding. Do we want that? Depends on the material, but generally no. For steel, you would assume full yielding. I'm not going to get into that at all because that's an entire nightmare in itself. Well, not that it's an entire nightmare, but I'm trying to keep things related to this class. So because of that, the Y should be chosen such that it creates the minimum value. So by using this larger value, it's going to reduce the maximum capacity of the bending moment. So yeah, you're right, Oscar, for that reason alone that it's further away. So 36 times 18.12 divided by 3.25 means that the maximum bending moment that we can have is 200.71 kip inches, which when you divide it by 12, you get 16.73 kip feet. Which means that no matter what type of load that you have applied for that beam, it cannot exceed a bending moment of that 16.73 kip feet. Any questions? No? All right. Let's reconvene in about another 5 minutes, and then I'm going to go into shear stress, just to show you guys how that works. Oh, I don't think I uploaded my lecture from last class, did I?
No.
I need to do that. I've just been so swamped lately. My bad. You guys will have that by tonight, tomorrow latest. If I do not send it by tomorrow, somebody shoot me an email.
Question.
Yes.
How did you calculate that, after you did the whole table, how did you calculate the IX?
The IX total?
Yes.
Well, when you get the table, you use what's called the parallel axis theorem. So you find the value of ADY squared, and then you find the value of IX. And so then the total cross-sectional moment area of inertia is just equal to we call it the sum of all of the IX's of each component plus the sum of ADY squared.
The 80, I guess my question.
That just relates distances into the stiffness.
Oh, okay. So, question, when you get the IX for the individual materials, how did you get that? How did you get that 0.3 and the 5.3?
That comes from the second moment area of inertia of individual shapes, which for that is going to be, for rectangular shapes, is BH cubed over 12. That,
That's where
comes from these equations here.
Oh, okay, so, okay.
Yep, that's your statics.
Okay, thank you.
All right, let's unfreeze this screen and get back to it. All right, so introduction to shear stresses. Shear stresses are another type of stress that you need to consider in the design of your beams. All right, let's consider a rectangular cross section, and it is subjected to some type of shear force, V. So that's our shear force. And let's say that this has dimensions of 4 inches and 2 inches. All right. Now, if this shear stress was equal to, let's say, 5 kips, what would be the conventional way of calculating stress in a beam for shear, for anything, not necessarily a beam? What do you guys remember about our shear stress equation from beginning of semester?
V over A.
Exactly, V over A. So 5 kips divided by 4 times 2, which would be 8 inches squared, which would just be 0.63 KSI. However, In reality, a lot of times when we are designing with shear in beams, we need to consider that there's actually some variation within the cross-section of the beam's shear. So, how will this look? This shear force is actually going to be quadratic, where it's actually maximum at the neutral axis. The way that we calculate this maximum shear stress is with a revised equation. Tau is equal to VQ over IB. V is the shear force, clearly. I is the second moment area of inertia. B is equal to the width at point of interest. And Q is equal to the first moment area above or below point of interest. So, what do we mean by this? What is this Q value? Well, when we develop a table, not even really a table, but this Q is equal to these new terms called A tilde times Y tilde, which A tilde and Y tilde are going to be the area above and below the point of interest and their location with respect to the neutral axis. So let's say that we wanted to find the shear stress here, tau. All right, that's where our point of interest is. What A tilde would be, oh, whoops, let me not stop recording on accident, go back to this. So I'm just gonna call it tau I. Tau I is our shear stress at the point of interest. This A tilde is going to equal the area above the point of interest. What is Y tilde? Y tilde is the location of the center of this area with respect to the neutral axis. This is basically the same as if you did the components, you have the A, and then you've got the Y, and then the AY bar. The Q is basically just this value, right? You're just doing it for a very particular location. So let's say that we were interested in the shear force, a distance, I don't know, Y 2 inches away from the neutral axis. All right? So what we would need to do is we know what our shear force is. We said our shear force was 5 kips. What is the width of the section at this location here? Yeah, it's just 2 inches. It gets a little more complicated once you start having like W shapes, because then the width varies. But the equation would just follow the same exact procedure. It's just a matter of understanding that width B. That's the trick with these problems. So you have B, which is equal to 3 inches in this case. But then what is the area? This A tilde here. What would that be equal to? first we need to know where this neutral axis is. Oh, well, I just realized this doesn't geometrically work. Let's make that 6 inches. So just change that from 4 to 6. So that way this is located 3 inches away, which in turn would make this equal to 12 inches squared, which 5 divided by 12 is just 0.42. Sorry about that. So, what is the area above this location here? Well, what we need firstly is the height. Let me actually just... the height of this location is going to equal what? Do you know? 1 inch. So, the total area, A tilde in this case, would be what? 1 inch times 2 inches, right? So it's 2 square inches. Now, where's the location of the center of that area?
It's just 2.5.
2.5 inches, yeah. Does everyone see how it's 2.5 inches? You go 2 inches up, and then it's halfway up the 1 inch dimension, so 2.5 inches. Which means that our first moment area of inertia is going to be 2 times 2.5, which is just 5 inches cubed. Now, we need I, which is just going to equal BH cubed over 12. So we've got 2 times 6 cubed over 12. Which gives us 36 inches to the 4th. So now we have everything we need. So we just throw in our shear stress. We get tau max, not tau max, but tau I is going to equal 5 kips times 5 cubic inches divided by 36 inches to the 4th, divided by 2 inches. Which gives us 0.347 KSI. Now, what if we wanted to find the maximum shear stress within the section? Because that's what we really want to design for. Well, in that case, for tau max, that would be our area, right? Because then our location of interest is at the neutral axis. And then we just need the center of this location. So, in this case, B would still be 2 inches because we're dealing with uniform thickness, right? Q would just equal half the area times a quarter of the height, because this value here, y tilde, what would that value be? It would just be 1 inch, right? So the Q would just be the, let me break it down actually. We have A tilde, which is just going to equal the 2 inch width times 3 inches, which gives us 6 square inches. The Y tilde is the distance from the neutral axis, which in this case is going to be 3 inches divided by 2, right? So 1.5 inches. And so Q is just equal to 6 times 1.5, which is 9 cubic inches. I remains the same. The only thing that's changed is the Q. So we can calculate our tau max, which is equal to 5 kips times 9 cubic inches divided by 36 inches to the 4th times 2 inches, which you'll notice is equal to 0.625 KSI. Why is this important? Because the 0.625 is greater than the 0.42 KSI that we calculated above. We call this the maximum shear stress, and this is the average shear stress. Any questions about anything I did here? Is everyone following along, or did I go a little too fast? Don't be afraid to speak out. No one? All right. So, that's just like an important thing to note, because like for concrete or for wood design, you want to use the maximum shear stress that you can get, because otherwise your section can potentially fail. Yes?
So, quick question. What is, we figured out for tau 1, or at that location, I guess, why would we have to know that instead of just doing the tau max, which is like at the 7?
It's not exactly to just know it. It's to be able to understand how the shear stress varies. So at certain points, the shear stress is going to be less than the average shear stress. And then at other points, the shear stress is going to be greater than the average shear stress. So it's just to show you that the shear stress in a section actually varies with respect to the height, which when you're designing for beams, a lot of cases, you usually want to consider the maximum shear stress. Now, there are certain exceptions. For example, for an exception to this rule is actually for W shapes or steel sections. So for W shapes, let's say we've got like this section right here. All right, so why is there an exception? Granted, if you were to draw out the shear area or the shear stress distribution, you're not going to get something as curved like this. Instead, what you're going to get is something a little bit more stepped, like this. And the reason has to do with that width B. Remember when I said in this equation that width B here? You would follow the same exact procedure that we had just done here, but when it comes to this, the B is going to be the width of your flange. So because of that, the shear stresses are significantly reduced. Does that make sense? Now, because of this, this is the true shear stress distribution. Where we'll have a tau max here. So what does this tell us? It tells us that the web is the one that's carrying most of the shear, right? So the flanges are what carry most of the bending capacity, and then the web carries most of the shear. Does that make sense? And because of this, with W shapes, when you are designing them, you actually don't use the entire cross-section. Instead, you actually use a simplified method where you just take the area of this web here, and we call this the average web shear approach. So instead of doing this massive amount of calculations, what would the area subjected to shear be equal to? What is the height of this cross section, of this section right here? Let's say that this is a, I don't know. I'm just going to pick something random. This is a W12 by 96. What would this height D equal to? Oh, wait. Is it that? No. Sorry. Ignore that. I got to fix this, I believe. It's literally called average web shear approach for a reason. Just use the web shear area. There we go. It's that. I'm going to call that dV. What would the height of that section be?
Which is the depth minus the thickness of the web.
Exactly. So it would be dV is equal to D minus 2TF. Where the depth for the W12 by 96 is 12.7 inches minus 2 flange thicknesses, so 2 times 0.9 inches, which is equal to 12.7 minus 2 times 0.9, which gives us 10.9 inches squared. And then to find the average web shear, it would just be the 10.9 inches squared times the web thickness, which is 0.55 inches. So roughly 6 square inches. And so to find the shear stress, instead of doing that entire process of VQ over IB, codes generally allow you just to use V over A. So if you had a shear force, V is equal to 10 kips, then this shear stress would just be 10 kips divided by 6 square inches, which would then give you a shear stress of around 1.67 KSI. Any questions about this? So really, to kind of go back to now this problem here, you might be wondering, why do we use the maximum shear stress here? Well, the reason that we can use the average web shear approach for steel is because of that steel curve. If you guys remember, steel will yield, which in turn allows you to be able to use more strength, right? Because it plateaus. You guys remember when we went over material properties, you had the stress strain curve, which this would have been like the shear normal stress and epsilon. Steel kind of looks like that, right? And it's very similar for shear. Well, materials unlike steel don't have that luxury of additional strength after they yield. They'll just fail, which is why you need to design for that maximum shear stress versus the average shear stress. So whenever you see a W shape, pay close attention to, whenever you see these types of problems for shear, pay close attention to the wording of the problem, because if it asks for the maximum shear stress, it's asking for what the shear stress is at the neutral axis, which for those sections, I will usually just give you guys something simple because I understand that this can take a little bit of time to do. So you guys will see that more often for rectangular shapes. If I asked you guys for like the shear strength of a W shape, usually I will specify average web shear approach, otherwise just assume it for W shapes. All right. Now, one thing to note is actually for like rectangles, what you'll find is that when you divide the max shear stress by the average shear stress, you actually get that the average shear stress, there's this relationship between them for rectangular cross sections. So if you think about it, as long as you apply a factor of safety greater than 1.5, preferably like 2 or larger, you're good, right? Yeah, you don't even really need to worry about the maximum shear stress. But then you got to spend more money. So it's a matter of really balancing out, going back and forth, trying to figure out what you're really trying to do. Is there any questions about anything that we've covered so far? No? All right. So instead, there is going to be one problem on your homework that you're probably not going to be able to do. So until probably like Tuesday. All right, so I would say focus on every other problem except for that problem explicitly. And we'll go over it on Tuesday. Not go over it, but like, I mean, it's going to be, yeah. So this is like your homework 8. I'm just showing you guys now. The first problem is just a neutral axis problem and second moment area of inertia problem. You guys, we covered this today. Second problem is the maximum bending stress, maximum shear stress using the general shear formula. So what I mean by this is just use tau is equal to V over A. No, I don't like the wording I did this. You know what? I might actually like rework some of this. So, yeah, just because the maximum shear stress using general shear formula, that's like using VQ over IB, which I might actually get rid of because I don't want you guys doing that for the W14 because that's going to be a very long problem. Yes?
We don't have class on Tuesday.
There's no class on Tuesday?
It's Veterans Day.
Oh, interesting. All right, so then I will have to probably remove deflections off of my exam because I had no idea. I thought Veterans Day was a Monday, but I guess I am just losing my mind.
Yeah, I just checked my calendar.
All right, I will have to send out a reminder then. Yeah, I'm actually going to probably rework this homework so that way, just to cover what we've kind of covered in class so far, just because I feel like I've been kind of rushing through the topics and the last thing I want to do is like throw too many things at you guys. So What I want to do now is like a full-fledged W-shaped design problem, including bending and shear. Now that we know how to do the checks. So, yeah, I'm going to work on the homework. So, problem 4 is going to stay. Problem 5 is going to stay. And problem 1. Problem 2 and problem 3, I'm going to replace them because I didn't get to them and I don't want to rush. And with Veterans Day being on Tuesday, I'm not going to be able to probably get to them. So that, and I also don't want to, like, honestly, I'm thinking about it more and I don't want to put deflection on the exam because it's going to be annoying. So that's going to be like on the last exam. So that's going to be covered probably for after the Thanksgiving break. Everyone okay with that? All right. So for this example, we have a W shape. All right. And let's say it has a point load located here and located here. And it's loaded 1,000 pounds on both ends. This is 5 feet, 15 feet, and 5 feet. All right. Now we want to size out what the W shape is going to be. All right. So, there are 2 ways we can determine our internal forces. First is just by drawing out the shear force and bending moment diagrams. You guys should hopefully know how to do that. Or you can use the tables because this is a simple load case. The load case that this would most match is figure 9. So M max is just going to equal, oh wait, I forgot to specify, A992 W shape, and let's put a factor safety equal to 2 on it. All right. So what is M max going to equal? It's going to equal the 1,000 pounds times 5 feet. So it's equal to 5,000 pound-feet. Does everyone see where we get that value? 5,000 pound-feet or no? M max is equal to P times A. All right. Now, for design purposes, we specified a factor of safety of 2. So we want to use a design force of 10,000 pound-feet because of that factor safety of 2 that we specified. All right. Yes.
Question: if one of those instead of being 1,000, was, let's just say 2,000, we would go based off of that greater one, no?
Say that again?
Like we have if one of the forces was 2,000,
Yeah.
we would use the greater force.
Not quite. You would need to, you would have an entirely separate shear force and bending moment diagram, which you would then either need to draw out the shear force bending moment diagrams, or figure 11 accommodates for 2 separate forces, which then you would need to follow the values for that. Make sense?
Yeah.
All right. So, with our design force of 10,000 pound-feet, you guys know how to determine the capacity in terms of flexure. So let's go ahead and do that really quickly. I'll give you guys a few minutes, figure out what the required W-shaped section modulus would need to be for it to be in flexure. Yes.
I have a question.
Mm-hmm.
So we have to convert, so you're using the, sigma equals m over s, right?
Yes.
So do you have to convert the 10,000 pound-feet when plugging it into the formula to find s?
Yes. Otherwise, you're going to get units of probably like feet cubed or something like that, which your tables aren't going to give you those.
What do we multiply that to convert?
M would need to be multiplied by 12, and then you would just need to know what your yield strength is,
Yeah.
and just know the conversion for that as well. Everyone figure it out yet? We're close. Not quite. 10,000 pound feet, and you're converting it to 12, but that's 50 KSI, kips per square inch. How do you get it to PSI?
Multiply it by 1,000.
Exactly. Yep, so you're close. I'll give you guys a few more minutes. How about over on this side? You guys got it yet? No? Alright. Got a size?
I'm not sure how to get the size, because I have the number, but how do I get the size then?
What's your number?
2.4,
Units?
KSI?
It's a multiplied by 2.
Oh,
Put this back here, see.
2.4. Alright, so 2.4 cubic inches, it should be cubic inches, because that's pound feet, then pound inches, divided by pounds per square inch, so that gives you inches cubed. So it's very small loads.
Don't you multiply by 2 for the factor of safety?
Yeah. So what would you guys use for the W shape?
I said W4 by 13
It's B4 by 13.
or W6 by 9.
Mm-hmm. Yeah, so, yep, so. Oh wait, no, you shouldn't have to multiply it by 2 because this is already the design force.
So you don't have to.
No, because this is what our bending moment was, so that's the times 2 for the factor of safety. Not that it affects anything. The loads are actually really small. So again, probably a fault of my own for the way that I made the problem.
But I still didn't make it.
You know what? Update this to be 10,000. And the reason for that is just so that way everything just add an extra 0. So this becomes 10,000 pounds, which makes this 50,000 pound-feet. And then this becomes 100,000 pound-feet, which makes the numbers a little bit more realistic. So that would make sigma is equal to my over I, or m over s. Your required section modulus is just going to equal the 100,000 times the 12 inches per foot divided by 50,000 psi. What do you guys get for a section modulus now?
24.
24 inches cubed? Is that what you get? All right. See, I'm so glad I'm able to resolve problems without having to manipulate the problem entirely. When in doubt, just add an extra 0. That's what I've come to learn for problems. Or removing a 0. All right. So, looking at this, what W shape would you guys recommend?
W12 by 22.
12 by 22? Yeah. All right. Let's work with a W12 by 22, which gives us a section modulus of around 25.4 inches cubed, which is greater than 24, with the factor safety of 2. All right. Now, we also need to know the design shear force. We need to check it for shear now. So, let's go back to our figure 9, and what is the reaction force for the beam? What is the design shear force we want to use? The shear force is just going to be the 10,000 pounds, right? Which that is going to equal the V from the table. But what's our design shear force? 2 times the shear V because of a factor of safety of 2. Same thing that we did here. So all your loads need to have a factor of safety associated with it, right? So our design shear force becomes 20,000 pounds. All right. Now, using the average web shear approach for W shapes, basically doing the same thing that we did here, confirm if the beam is adequate in shear also. Take a few minutes to do that, and then we'll go over it. I'm not going to give you guys a get out of jail today either, because I realize that beams have been a little bit hectic because I've been low-key trying to figure out what I want to teach and not what I want to teach while I've been going along. So So I feel like you guys just having to deal with me this week has been punishment enough. All right. And I just reworded problems 2 and 3 so they weren't asking what they were asking. So now everything you should be able to do on the homework. So no excuses this time. And I'm recording this, so it's on record. Everyone can now do all of the homework problems. There we go. Oh yeah, November 11th, no classes. Man, I'm gonna miss you guys. All right, I'm gonna give you guys a take-home, get out of jail. That would be too mean, right? All right. Yes.
Would you use the 10,000 or the 20,000 pounds for V?
What are you designing for? The 10,000 pounds doesn't accommodate the factor of safety, whereas the 20,000 pounds does. So
if you're solving for tau, you would use 20,000?
You would use 20,000, yes. And does it give allowable shear strengths in here? I believe so, right? Yeah, yield strengths and shear. Mm-hmm. Which it doesn't say on the table, actually, now that I'm thinking of it. But a good rule of thumb is the yield strength of in shear, or, hold on, wrong symbol.
It's frozen.
Oh, it would help if I, yeah, sorry. I'm like trying to do like 4 things at once. I'm like trying to balance between like now reorganizing the schedule, because I don't want to put deflection on the exam anymore, because I want to do more shear problems next class. So a good rule of thumb, since it doesn't specify on the table, but for steel explicitly, the shear strength is usually 60% of that. It's just a good rule of thumb. So you can kind of even see the relationship on the table. 60% of 36 is 21.6, which they just round down to 21. So for tau y, use, if this is 0.6 times 30, or no, 50, then it's 30. So, did you guys compute the shear stress yet in the beam using average web shear? You guys should have hopefully been able to do that. Question over there? You think you got it? All right. How about anyone else? Anyone else get it? You too? What? Half? All right. So, what we are using a W12 by 22. What is the shear area for the W12 by 22? It's the area of the web. So what you need to do is you need the depth of the web, which the depth of a W12 by 22 is 12.3 inches minus 2 times the flange thickness, which is 0.425 inches. Which gives us a total shear depth of around 11.45 inches. And so then the shear area is just going to be that 11.45 inches times the web thickness, which is 0.26 inches, which is 2.977 inches squared, which means that tau is equal to the 20,000 pounds. I'm going to write it as 20 kips divided by 2.977 inches squared. So we get a shear strength of 6.72 KSI. Is our beam good for shear? Yes, because it's less than 30 KSI. So, I still have 2 minutes with you guys. Time for you to get out of jail. I'm kidding. I'm not going to do that. But it's just a good rule of thumb. So, here's an important thing to note is when you have relatively long spans, bending usually governs. Which means that for most beam problems, figure out the flexural demand and size your beam based off of flexure, and then check shear. For shorter spans, usually shear governs. So rule of thumb is usually check bending first. Because the beam usually needs to be a really small span in order for shear to govern. Because otherwise, 90% of the time, bending is always going to govern. So whenever you're designing a W shape, always look at how flexure is affected. All right. It is now 8:15. You all are free to go without a get out of jail. And like I said, I changed that problem too. I removed one of the things, just maximum shear stress using the average web shear approach, and then just determining the maximum shear stress in the box shape. So this is using that VQ over IB stuff. All right. Have a good night.